and also my first time to use a bamboo pointer stick. So in a talk, so I'm kind of excited about that. Okay, so yeah, I want to talk about some of the work that I've done with a number of collaborators, including Jinwei, who's here, and also Hao Li and my PhD student from Tsinghua, Valerii Sopin, on constructing tensor categories of modules for the Virasoro algebra using vertex algebraic methods. So just write the definition of the Virasoro algebra here. I guess people here probably know the definition of the Virasoro algebra and how it's important in conformal field theory. So I don't think I need to say too much about that. So we want to look at modules of a fixed central charge C, and maybe the physics motivations. You want to build some conformal field theories out of some nice modules for the Virasoro algebra at a fixed central charge. So either consider the chiral side of a CFT, or maybe go farther to build full CFT. The VOA techniques are especially suited for understanding the chiral half of a CFT. And so in CFT, of course, you have this idea of fusion, and that should correspond to a tensor product operation on modules for the Virasoro algebra. And the important thing to remember is that this is not the vector space tensor product of Virasoro modules. As a Lie algebra, of course, you can take a tensor product of modules and get a new module, but that's not going to fix the central charge. That's definitely not what we're talking about. So let me introduce the kinds of modules I want to be talking about. So let's start with the Verma module, VCH at a fixed central charge C and a lowest conformal weight H. So you take a one-dimensional space where the central element of the Virasoro acts by C, the L0 operator acts by H, and then Ln acts as 0 for positive n. And then you induce to a module for the full Virasoro algebra, and it has this PBW basis of monomials of negative Virasoro operators applied to this lowest weight vector. And if you want to make this a basis, then you require that some ordering of the monomials. So those are the Verma modules. For most values of C and H, the Verma module is irreducible. Generically, this is irreducible. But for every value of C, there are countably many exceptions, and those are, you can find those exceptions by writing the central charge in this way as 13 minus 6t minus 6t inverse. And then writing down these HRS conformal weights in terms of positive integers R and S. If you write down this conformal weight, then from the determinant formula for the Virasoro algebra, these are the places where you get reducible Verma modules. So now let me use LRS as notation for the unique simple quotient of the Verma module with this lowest conformal weight. And I won't include the C in the notation because the C will usually be fixed and understood. So these cover all of the simple highest weight modules at central charge C. And now if you want to construct a CFT from some collection of representations of the Virasoro algebra, then you want to essentially come up with an appropriate category of modules. So roughly from the physical language, what is the spectrum of this CFT that you want to build? So at this conference, we've heard a lot about the Liouville CFTs. If you want to work with the Liouville CFT in the usual way with unitary representations, then the spectrum is going to be all, the irreducible modules will all be Verma modules. From the vertex algebraic point of view, Verma modules for the Virasoro algebra are quite large in some sense, and therefore their fusion products will also be quite large. You'll get some kind of non-discrete thing like a direct integral if you try to fuse two Verma modules. And unfortunately, when we use VOA methods to study CFT or the Virasoro algebra, we haven't really developed the right methods for handling these kinds of non-discrete tensor products. Instead, these modules work very well when the fusion, in situations where the fusion is going to be some kind of discrete module. So then, motivated by that, let's define this subcategory. Call it OC for a fixed central charge C. It will be all of the Virasoro modules that you can build up from these irreducible modules which are not Verma modules. So you look at all the modules with a finite Jordan-Holder composition series, where the composition factors are coming from these. So we do not consider any Verma modules in this category because either they are simple and the composition factor is not one of these, or they do have these composition factors, but they have infinite length. So then they're still not in the category. So yeah, yes.
Sorry, maybe I misunderstood. At the generic central charges, even the Verma module, even a reducible Verma module would have finite composition, the composition length too.
Yes, and that right. That's the yes. Yes, that is true. Also, you can get Verma modules with finite length, which are not irreducible. In those cases, you will always have an irreducible Verma submodule. So that will not be one of these composition factors. So yes, you could have a finite length Verma module with several composition factors like this, and then one irreducible Verma composition factor. That's also possible. Yeah, so that happens for the
I see. So
negative RS, right? It will be negative RS.
So it will be a negative RS type of module.
You want only positive.
Okay. Thanks.
So yes, that will happen when the T parameter is irrational or when the T parameter is a negative rational number. So this is a category we want to work with in this talk, and it's well suited for the vertex algebraic methods that we have developed so far. So maybe I'll just say a little bit about some of the background of vertex algebraic tensor categories. So maybe on the physics side, it goes back more or less to Moore and Seiberg, who observed that the fusion in a rational CFT should have some kind of nice structure, which was later mathematically formalized as a definition of a modular tensor category, or maybe modular fusion category, if you want to distinguish between semi-simple and non-semi-simple. On the VOA side, there's Frenkel, Huang, and Lepowski defined intertwining operators and fusion rules, which will be a key element in the construction of tensor products for fusion tensor products for VOA modules. Maybe the first examples of non-trivial braided tensor categories that were constructed that are essentially VOA tensor categories were what Kanjan and Lustig did in the early 1990s, where they constructed representation braided tensor categories from affine Lie algebras at most levels. So these are corresponding to like the WZW models in physics, except they were not studying the levels that are relevant for rational WZW models in physics. And then that kind of their construction motivated Huang and Lepowski to develop a general theory of tensor categories for modules for VOA. And the theory they developed at that time was good for rational VOAs, rational CFT. So in particular, they were able to apply it to these rational WZW models in physics. But at that time, they didn't really have a good theory for handling non-semi-simple, especially logarithmic CFTs. So more recently, they, along with Lin Zhang, they developed a generalization to tensor categories, which could possibly have logarithmic modules, which is relevant in logarithmic CFTs. where correlation functions could have logarithmic singularities. That's the logarithmic singularities tell you that the Virasoro L0 is acting non-semi-simply, and therefore you are definitely not working with rational CFTs where everything is semi-simple. So let me now discuss this definition in terms of intertwining operators. So the way they defined fusion tensor products of modules for VOA, here let me write it to make things a little bit more simple. Let me restrict to Virasoro VOAs. They defined these fusion tensor products in terms of what they called intertwining operators, but these really should correspond to what would be called vertex operators in a CFT. So for any three modules, let's say in this case, these modules are coming from this category OC that I defined already, then an intertwining operator is a linear map from the tensor product of the first two modules to a space of formal series with coefficients in the third module, where the series allow arbitrary complex powers of the formal variable x, and then finitely many positive integer powers of the logarithm. So that's the logarithms are designed, are included so that we can handle logarithmic CFTs. Maybe the first important property that an intertwining operator has is this L-1 derivative property. L-1 is, if you put the L-1 operator inside the intertwining operator, it should give you the derivative. And this is an extremely crucial property that we want to use if we want to derive BPZ equations from intertwining operators using null vector relations, the module for the Virasoro algebra. And then there are these two other properties of an intertwining operator, a commutator property that tells you how the Virasoro operators commute with the intertwining operator, and also an associator formula that tells you if you put a Virasoro operator inside, then it can be pulled out on either side in this kind of way. So these properties are, I think, are also pretty well known in the physics CFT literature. But this is the mathematical definition of intertwining operator that's supposed to capture those properties of vertex operators in a CFT. And then you can think of an intertwining operator as somehow